Hey everyone, let's get started with linear regression, the first model that we are going to learn about. So far we have discussed about Python, we have discussed about NumPy, Pandas, Matplotlib, Seaborn, we have discussed data preprocessing, data visualization, we also discussed the machine learning jargons. Now it's time to start with our first model, which is going to be linear regression. So, first of all, we already discussed what supervised learning means. Supervised learning means that we have labeled data. That is, we have some independent attributes and then we have a target attribute. So these are the independent attributes and this is the target attribute, Y. Now, supervised learning problems can be of two categories. One is classification, other one is regression. Classification means when your target attribute is going to be a categorical variable, that is, it has some fixed categories. Whereas in regression, when your y is a continuous variable, it is going to be a problem of regression. So if we see our data set and we say that the target is salary, salary is a continuous variable which depends on gender, SSCP, SSCB, HSCP, and so on. So this salary is a continuous variable and it is a target variable. So if salary is a target, then we basically have a regression problem in hand and we are going to solve it using regression model. Okay, does that make sense? So when your y is a continuous variable, then we have a regression problem, and now we're going to understand what linear regression means. Linear regression means that our y is linearly dependent on x1, x2, x3, and x4. So the model that we will get is y is equals to w0 plus w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. So in this case, W0 is called the intercept and the W1, W2, W3 and W4 are called the coefficients. All of these are constants, right? And if we have a model like this, this is called linear regression model. And here our y is linearly dependent on x1, x2, x3 and x4. So once we have the coefficient and the intercept values, that is, once we know what W0 is, what W1 is, what W2 is, what W3 is, and what W4 is, our model is ready. So if let's say our W0 is 2, W1 is minus 2, W2 is 4, W3 is minus 1, and W4 is 6, then this is our linear regression model. Does that make sense? Now, linear regression can be of two types. First is simple linear regression, and the second one is multiple linear regression. So in simple linear regression, what happens is we just have one independent attribute and one target attribute. So here the model would look like y is equals to w0 plus w1 x1. So w0 is the intercept, w1 is the coefficient. Whereas if let's say we have three independent attributes and then one target attribute, in that case, our model would look like this. So basically, since we have three features, three independent attributes, so the model looks like this. And in multiple linear regression, what happens? We have multiple independent attributes, whereas in simple linear regression, we just have one independent attribute. So these are the two categories of linear regression. To understand things in a better way, let's start off with simple linear regression because in everything was going to be similar, right? So let's do it in a simplistic manner. That is, we have one x and one y. Everything that we do here, it's going to be the same for multiple linear regression also. It's just that it's easy to visualize when we have one independent attribute. So we have x and we have y. So let's say basically this is our scatter plot of x versus y. Okay. Now, how will the model look like? The model will look like y is equals to w0 plus w1 x1. Okay, this is how our model looks like. Now, let's say this could be our model because this is a line, right? So this could be our model. This also could be our model. Our model could be this as well. Our model could be this as well. So multiple options, there are infinite possibilities. So basically all the lines are, are, are linear lines or straight lines. It's just that the coefficient values would differ. For this orange line, the value of W0 and W1 would be different. For this blue line, the value of W0 and W1 would be different. For this purple line, the value of W0 and W1 would be different, and so on. But which would be our model? Our model would be the one which fits the data the best, which gives us the least error. Now let's try to understand more on that. Let me just create a few points only. Okay, let's create a few points. Now, let's talk about one line. Let's talk about this line. Now, if you consider this point, this is the x value, and this is going to be the y value. Okay, this is going to be the y value. So this is basically our y actual for this point, right? Now, if let's say this purple line is basically y is equals to 2 plus 3x, just putting this randomly, then if we put the corresponding x here, let's say the x value is, let's say, a here, and the y value is ya. So if we put x as a, we'll get 2 plus 3a. So basically our model is going to say that the value is going to be 2 plus 3a. Let me write it as y predict. Now the difference between this y actual and y predict should be less. And what will be the y predict? The y predict would be basically wherever this x intersects with this model, purple line. So this is going to be y predict. Okay, this is going to be y predict. Then this difference, so this ya basically means this is the actual value of our, our data point. This is the actual y value of our data point. Whereas y predict is basically the prediction that our model gives. The model which is 2, y is equals to 2 plus 3x, the linear model, right? So the error is written as y actual minus y predict. The error is y actual minus y predict. Okay, we have to minimize this error. Obviously, we want our predictions to be as close as to the actual values. So we have to minimize this error. But we don't have to minimize this error only for one point. We have to minimize this error for all the points. Now, no matter if the error is positive or negative, it is an error. If y actual is greater, then error will be positive. If y predicted is greater, then error will be negative. But both of them are errors, and we are concerned with the magnitude of error. We are not concerned with their signs. It does not mean that if, let's say, here we have some points below the line, some points above the line. So there will be some positive errors, there will be some negative errors. And if we add all of the errors together, the positive errors and the negative errors will just cancel each other. And probably we'll get an answer very close to zero. But that does not mean we don't have the error. We definitely have error, and we have error in all the points. So that's why we only are concerned with the magnitude of errors. So what we do is we find out the errors for all the points, let's say for point 1, and then we just square the errors so that we are only getting the magnitudes for all the points and then sum it over. So what we are doing is, obviously we could have used mod as well, but the calculus with square term is easier as compared to the mod. That's why we take the square term. So basically we have y actual minus y predicted whole square summation. So basically for all the points, we figure out y actual minus y predicted whole square. So this is the error. So this is the total error. And remember, we are only building the model on the testing data. So here the data that we have, the points that we have are only on the training points, not the testing points. They are only and only the training points. So we are building our model on our training data. We are going to test it on our testing data, but the model will only and only be built on training data. So remember, we were dividing our data into two sets. One was the training data, other was the testing data. On training data, we are building the model. On testing data, we test the model. So to build the model, we are only going to use training data. So the points that I have mentioned here are only the training points. So now this is the error, and this is the error we want to minimize. So any line which gives us the least error is going to be our best fit line. So here we talked about multiple lines, right? We are going to find out the error for all the lines, and whichever line gives us the minimum line, whichever line gives us the minimum error, it's going to be our best fit line or our linear model. So we are only interested in that line which gives us the least error. Now, how do we figure that out? Obviously, there is mathematics involved, but I'll try to give you a gist of it. So basically, this is a optimization problem that we want to solve. This is the optimization problem that we want to solve. That is, we want to minimize this. So basically, we try to minimize this using differentiation and calculus. And in the process of minimizing, we will get what are the W0 and W1 values which give us this least term, which give us this least error. So basically, we will try to minimize this and we will figure out what are the W0 and W1 which give us the least error. And those W0 and W1, let's say the W0 comes to be 2, W1 comes to be 3. So our best fit model or our linear regression model becomes y is equals to 2 plus 3x. So this is how we get our model. So first we have the training data. Then what do? Is we try to figure out what is the cost function or the error function that we are trying to minimize. Then we solve that optimization problem and then find out our constants, which is this intercept plus the coefficients. And once we have the intercepts and the coefficients, our model is ready. Okay, so y is equals to 2 plus 3x would be our model if 2 if w0 is 2 and w1 is 3. So basically, after we solve this, that is after we solve this optimization problem, we get the w0 and w1 which give us the least error, and the line which gives us the least error is our best fit line or our linear model. Okay, now this is something that we already have covered. So a linear regression model's aim is to find the best fit linear line and the optimal values of intercept and the coefficients such that the error is minimized. Error is the difference between the actual value and the predicted value, and the goal is to reduce this difference. So basically, this is the error term that we talked about. This is the y actual, whereas this is the y predicted. So the difference between them is the error term. And error is called y actual minus y predicted. It's also called the residual. So error is equals to residual. It's equals to y actual minus y predicted. Errors can be positive as well as they can be negative. So what we have to do is we have to square the errors for all the points and sum it over. So here what is yi? Yi means y actual and yi cap means y predicted. Okay. The vertical distance between the data point and the regression line, that's the difference between the y actual and the y predicted, is called the error or the residue. Now we will move on to the assumptions of linear regression. Okay. Now, obviously, linear regression has a few assumptions. Like, if we want to build a linear regression model, then our data set should obviously be linear. The first thing is that, but there are a few assumptions also. There are other few assumptions. So we'll discuss all of them. Obviously, we should take care about these assumptions, but generally, what people do is that they build a model and check if we are getting decent results with the model, that is, if our testing data is giving decent results, then we are good with this model. Otherwise, we can change the model. But the assumptions, if you see the assumptions, or if you try to figure out if there's linearity in the data, if there is homoscedasticity in the data, and so on, then you will be able to figure out is linear regression going to be good for your data set or not. Okay, I'll talk about more on this after we deal with all the assumptions. So the first assumption of linear regression is that the independent attributes should be linearly related with y. That is, y should be linearly dependent on x1, x2, and x3. So basically, the dependent variable y should be linearly related to the independent variables. And this assumption can be checked by just drawing a scatter plot between the variables. So for example, let's see. If this basically on our y-axis we'll have the target and the independent attribute on the x-axis. If the data looks linear like this, that is, there seems to be some positive relationship, or there seems to be some negative relationship, that is positive or negative linear relationship, then we can use linear regression. If there's some polynomial relationship, that is, it's not exactly linear, in that case probably linear regression is not the right model for your data set. So if the data seems to be linearly related, that is x and y seem to be linearly related, then linear regression should be used. Otherwise, there's no point of using linear regression. If your y is not linearly related to your independent attributes, then why are you even applying linear regression, right? Now the second one. So once you have a linear regression model, you've built a linear regression model, you should see the graph between the errors, that is the residuals, that is y actual minus y predicted versus the y predicted. So the errors, they should be in a constant range, or you can say they should have constant variance. That is, they should not have an increasing or decreasing trend as the y predicted increases. So if we have the errors in this way, that is, they have constant variance or they are in a constant range, then then our linear regression model is probably the right model. So this property, that the errors, they show constant variance or they are in a constant range, and they are not changing, they are not increasing or decreasing with the y predicted, that property is called homoscedasticity. So homoscedasticity means the variance of the error terms should be constant. That is, they have constant variance, or the spread of the residuals is in the same range, or it's constant. Okay, that's called homoscedasticity. Now, if you see these two, now here the residuals are showing an increasing trend. That is, they are increasing as our y predicted is increasing. Or here, our residuals are showing a decreasing trend. As our y predicted is increasing, our residuals are decreasing, right? So this increasing trend or this decreasing trend, these both are not acceptable. That is, they don't follow homoscedasticity. That is, they follow heteroscedasticity. So the assumption of linear regression is that the residuals should have constant variance. That is, the residuals should not be affected. They should not increase or decrease if our y predicted is increasing. So if we have our residuals like this, then linear regression is probably the right model. If we have things like these, that is, we have heteroscedasticity, that is, the residuals are showing an increasing or a decreasing trend, then then our model, then probably linear regression is not the right model. Now, the error terms that we have, that is the error terms, that is the residual terms, that is y actual minus y predicted for all the points. For all of these points, these error terms should not be related to one another. They should be not correlated. They should be independent of one another. That's our third assumption. And these error terms, they should be normally distributed. What does a normal distribution mean? A normal distribution means it's a symmetric bell-shaped distribution. That is, it would be symmetric about its peak. So whatever is to the left will exactly be the same to the right. So the left and the right are mirrors of one another about this peak line. So this is a bell-shaped curve. Looks like a bell, right? So what we are saying is that the error terms, these y actual minus y predicted, these error terms, they should come from a normal distribution. So if we draw the kernel density estimate, what is kernel density estimate? Kernel density estimate is basically the approximate distribution from which a particular feature or a column is coming from, right? So basically, if we draw the KDE, that is the kernel density estimate, that is we basically try to plot the approximate distribution from which our error terms are coming from, then it should actually be a normal distribution. So the KDE, the kernel density estimate, or the approximate distribution from which the errors come, should be a normal distribution. That is the fourth assumption. So this you can figure out once you have created your model. And then you should figure out, are your errors actually normally distributed, are they related or not? And the ideal conditions for linear regression are that the errors should be normally distributed, and the second is that the errors should not be correlated to one another. Now, moving on to the last assumption, which is no multi-collinearity. So first, let me explain you what multi-collinearity means. So what we want in linear regression is that our y should be linearly related to x1, x2, x3, and so on, right? That's the first assumption that we talked about. The assumption was linearity. The last assumption that we have is that these, if we are calling them as independent attributes, they actually should be independent. That is, they should not be related. They should not be correlated. So the independent attributes should not be correlated. So basically x1, x2, and x3, these independent variables should actually be independent. That is, there should not be any correlation between the independent variables. And what is multi-collinearity? Multi-collinearity. Multi-collinearity is the condition when the independent attributes are correlated to one another. And we don't want any multi-collinearity in linear regression. That is, our independent variables should actually be independent. There should not be any correlation between the independent variables. Now, let's say if multi-collinearity is not satisfied, then what should you do? First thing is do nothing. Basically, check, build your model and see if you're getting decent results. Build your linear regression model and see if you're getting decent results. Then go ahead and use that model. If not, then go back, improvise your model, remove multi-collinearity, or maybe change the model. Second thing is remove some of the highly correlated independent variables. For example, if x1 and x2 have a Pearson correlation coefficient as 0.9, then just probably use one out of them. Remove x2 column, or remove x1. It depends on you which one you want to remove. So remove one of the highly correlated columns. That is, either remove x1 or x2 if both of them are highly correlated. Or if you don't want to just remove one of them, you're confused, you don't want to remove either x1 or x2, then what you could do is, instead of x1 and x2 using both of them, instead use a new feature. That is, derive a new feature by linearly combining the independent variables, such as adding them together or performing some mathematical operation. So basically, either use instead of x1 and x2, use x1 plus x2, or maybe x1 plus 2x2, or 3x1 plus 2x2. It depends on you which you want to use, right? Third thing that you could do is third thing is basically have linear combination of the correlated variables. What's the fourth thing? The fourth thing is perform a analysis designed for highly correlated variables, such as principal component analysis. So basically, what we'll do is in PCA, we have x1, x2, x3, and y. So what you'll do is first take this data set and you convert it into principal components, PC1, PC2, PC3. We'll discuss principal component analysis in detail in one of the lectures, one of the last lectures, but I'll explain you in brief. We have already touched based on principal component analysis once. So what do we do is we convert these three features into new three features. And what happens is the highly correlated variables, they actually they align in one of the principal components. So essentially, this principal component will carry maximum information, let's say 60%. This is going to carry, let's say, 30% of the information, and this one is, let's say, going to carry 10% of the information. So the first principal component will actually carry maximum information of the data, followed by second principal component, followed by third principal component. And then maybe if you want to use just first two out of them, use these two, because your 90% of the information of the data is being captured by the first two principal components. So basically, in principal component analysis, generally it's used for dimensionality reduction, and one other advantage is that all the highly correlated variables, they align in one of the principal component. Okay, so these are the 5 assumptions of linear regression. Let's revise them. So first is linearity, that is basically, your y should be linearly related to your independent variables. The second is that the residuals should have constant variance, or also called as homoscedasticity. That is, they should have the property of homoscedasticity. The third is that the errors should not be correlated to one another. And the fourth is errors should be normally distributed. The fifth is that the variables, that is, the independent variables, should actually be independent, and there should not be any correlation between the independent variables. Now, let's say, let's say you are building your linear regression model. Obviously, it would be good to check for the assumptions of linear regression, but let's say you build the model, even if some of the assumptions are not satisfied, and if you're getting decent results with your linear regression model, you wanted, let's say, the let's say some evaluation metrics. I don't want to use the word accuracy here. So let's say you wanted decent results, and you got decent results, or you even got the results better than what you asked for. If your model is able to perform well on the testing data, then probably you should go ahead and use the model that you have built, even if some of the assumptions of linear regression are not satisfied. But if you feel that your model is not performing well on the testing data, then you should come back, check, or check if linear regression can actually be used, or you should go ahead and use another model, or you should do some pre-processing, or you should remove the highly correlated variables, and so on. Okay, so essentially these assumptions of linear regression are going to just help you figure out whether linear regression is the right model for you or not, whether linear regression should actually be used in this data set or not. So these assumptions are going to give you a hint on that. But obviously, every data set is different. You have to build the models and see which is a good, which is basically turning out to be good for this data set, which is turning out to be bad for this data set. Okay. So these assumptions are just going to give you a hint. Okay. Now let's say you have built the model. So now let's assume, let's go back to our simple linear regression where we had one independent attribute and one target attribute. In that case, let's say you built the model on the training data. and the model turns out to be y is equals to 2 plus 3x. So this is your linear regression model, the best fit line, the one that minimizes the error for the training points. Now, this model is built on the training data. Obviously, it has to be tested on the testing data also. Now, we test the data and we calculate some evaluation metrics. So what are these evaluation metrics? These evaluation metrics basically help us evaluate our model on the testing data. So metrics which help us evaluate our model on the testing data are basically called evaluation metrics. And for linear regression or for regression, these are the four metrics that we have: R square, adjusted R square, MSC, and RMSC. Since MSC and RMSC are simple, I'll first go with those. Okay. So let's say the testing points are 2, 1, 0, 4, 3, 2. So these are the testing points that we have. So basically on the training data, we build the model and we got the model as y is equals to 2 plus 3x, and then we have the testing points. Okay. Now, if you see, we have to, what is the mean square error? It is very similar to the cost function that we talked about. The mean square error is basically take the sum of square of errors, that is summation y actual minus y predicted whole square, and then you take the mean square error. That is, you just have your sum of square of errors and you divide it by the total number of points. So mean square error is 1 by n summation y actual minus y predicted whole square. Okay. So for the first point, what is y actual? So for this testing point, the y actual is 1, right? So number of points that we have, the number of testing points we have is 3. Okay. So the first point, the y actual is 1. What will be the y predicted? The y predicted, how are you going to figure out y predicted? Substitute 2 in place of x. So 2 plus 3x, which is going to be 8, right? So basically the prediction for this point is going to be 8. Okay, so we do y actual minus y predicted whole square for the first point. Then for the second point, what is y actual? It is 4. Then what is y predicted? Substitute the value of x in place of, substitute basically 0 in place of x. So 2 plus 3 into 0, which is 2. Plus y actual is what? It's 2. Then what is going to be y predicted? Again, substitute 3 in place of x. So 2 plus 3 into 3, that is 11. So if you figure out this value, it's going to be 1 by 3, 49 plus 4 plus 81. So it's going to be 134 by 3. So this is going to be your MSC, mean square error. Now, since this is the error, do you want it to be high or low? We want it to be as low as possible. The lower the error, the better is our model. Okay. So MSC is basically this. So we want it to be as low as possible. And what is RMSC? Root mean square error. Basically, take the under root of mean square error. Right? Again, why do we take root mean square error? Because if you see, this will be, if the unit of y actual and y predicted is unit, let's say u, then the mean square error will have the unit u square. So the unit is not the same. So to have it in the same unit, we'll basically have RMSC, so that the y actual, y predicted, and the error all have the same unit. Okay. So again, RMSC should be high or low? It should be low because we want the error to be low. So those are the two evaluation metrics that we have for linear regression. So lesser the MSC, lesser the RMSC, better is our model. Okay. Now let's move on to what is R square. R square is also called as coefficient of determination. This is the most commonly used metrics for model evaluation in regression analysis. And the value of R square is generally between 0 to 1. 0 and 1 both included. And the value closer to 1, the better is your model, the better fit it is the model, the better the model fits the data. Okay, so R square is also called goodness of fit. Basically, it tells how well your model fits your data. Okay, so a few points before I explain what R square is. A few points are that R square is called the coefficient of determination. It is also called the goodness of fit. It's going to be the value lies between 0 to 1, and it tells how good or how well your model fits the data. Okay, now let's understand this with help of an example. So let's say these are the testing points that I have, and I already know my model. I have found the model from my training data. So basically this is the model. Okay. Now in R square, what I do is I compare my best fit model with my mean model. What does mean model mean? I'll tell you. First of all, let's try to find out the variance about the line, best fit line. So what is the variance about the best fit line? The variance means basically the error terms. You just square the error terms. So if you see this point, the y actual is this, whereas the y predicted is going to be this. So this is the error. So you square up all the errors. You find all the errors and you square them up for all the points, and that's going to basically give you the variance about the best fit line. So what is variance about the best fit line? It's the sum of the square of the errors for all the testing points. Okay. Now let's figure out the y's. Obviously, the y's are these. Try to figure out the mean y value, whatever is the mean y value, the actual mean y value, right? So for all the points, you know the y, and then you just figure out what is the average y, and that is going to be your mean line. So basically, that's the line in which you are trying to say that, hey, the prediction is always the average y, the average y. So that let's say this is the mean line. Now again, you find out the variation about this mean line. You find the errors and then you sum up the square of the errors. So first you find the errors, square them up, and sum them over. So that is going to be the variation that I have about the mean line. Obviously, the variation about the best fit line should be less, right? Because it's the best fit line that's the model that you have made on your training data. So the variation or the error should be less. So what is R square now? R square is 1 minus variation about the best fit line by the variation about the mean line. Okay. So the variation about the best fit line should be less, or the variation about the mean line should be less. The variation about the best fit line should be less, right? So let's see. Let's see an example. We have mouse size, which is on the x-axis, and we have the mouse weight, which is on the y-axis. So mouse weight depends on the mouse size. Okay, let's say this is the best fit line that I have, and this is the mean line, right? So the variance about the line is 6, right? It's 6, and the variance about the mean line is 32. Again, how can I write this? I can take the LCM, right? So it will become variance about mean line minus variance about best fit line by variance about the mean line. Okay, that's how it's written here. So variance about the mean line definitely should be more, because your best fit line is basically the line which is fitting your training data the best, right? So ideally, the variance about the best fit line should be less. So variance about the mean line is 32, variance about the line is 6. You do it and you get your R square to be 0.81. So this means that your best fit line is fitting the data well. It's fitting the testing data also the well. So basically, you build the model, you build this blue line on the training data, and now when you're checking it on testing data, it is fitting your test, it is fitting your testing data also decently. So your R square is 0.81. But if you have a very bad model that you have built on your training data, then what happens is your variance about the line is also high. If you see, this blue line is not very close to all the points, right? For all the points, we'll have a lot of error. So the variance about the mean is 32 and variance about the line is 30. So variance about the mean line is 32 and variance about the best fit line is 30. Now, if you see, your R square turns out to be very less. So what we want is that the variance about the best fit line should be less. In that case, only our R square is going to be more. So the model that you have built on your training data should fit your testing data also very well. If it fits your testing data very well, then your R square is going to be very close to 1. Okay, so what we want is that our R square should be very close to 1. Okay, let's quickly revise what R square is. R square is coefficient of determination. It tells the goodness of fit or how well the data, how well the model fits the data. Okay, and that's pretty much about R square. Okay, that's the third evaluation matrix that we studied. Now, there is something called the as adjusted R square. Basically, it's an improvement over the R square. So what happens is if the number of features increase, our R square actually is very high. That is, it's very close to 1. It gives us the illusion that we have made a great model. So the illusion might be wrong because it may happen that we have not built a very good model. But just because the features are high, that is the number of features are high, our R square is high. So that's the drawback of R square. It tends to increase as the number of features increase. Okay, so R square tends to increase as the number of features increase and it gives us the illusion that our model is good, whereas actually it is not. So when the number of features are high, you shouldn't go for R square, but you should go for adjusted R square. And we'll see what adjusted R square is. It turns out to be lower than the R square, but it basically decreases that part. It basically reduces the effect of the number of features which is there on R square. So whenever the number of features are high, you should go for adjusted R square. Okay, now let's see what the adjusted R square formula is. Okay, so let's say we have got R square on the data. We have first figured out our R square, right? And the number of features, number of independent features that we had were, let's say, 100. Okay, and the total number of points that we had were 1 lakh. Number of records that we had were 1 lakh. So what should, how will your adjusted R square be calculated? So adjusted R square would be 1 minus the R square that you have already figured out into n minus 1. N is basically the total number of records that you have. That is 1 lakh minus 1 divided by n, that is the total number of records that you have, minus the independent features that you have, which is 100, minus 1. So this is going to be your adjusted R square and it turns out to be lower than R square. So if you have your R square and the total number of records that you have is n, the total number of records is n, right? And your p is basically the number of independent variables, then your adjusted R square turns out to be 1 minus R square into n minus 1 divided by n minus p minus 1. Okay, that is what your adjusted R square is. And it turns out to be lower than R square, and this should be used when the number of features are high. Because when your features are high, R square is automatically high, maybe giving us an illusion that that the model is good, but maybe it's not good. It's just that the number of features are high. Okay. Let's talk about, now let's revise a bit, okay? So first question, which one is the disadvantage of linear regression? The first one says the assumptions of linearity between the dependent variable and the independent variables. In the real world, the data is not linearly separable. Yes. So obviously, it's very hard to get linear data, right? In real world. That's correct. The second option is linear regression is very sensitive to the outliers. Yes, linear regression would be sensitive to the outliers. The reason is because here we are calculating summation y actual minus y predicted for the training points, for the testing points, right? So for training points, we have summation y actual minus y predicted whole square, and this is the thing that we are trying to minimize, right? So if we have outliers, the y actual minus y predicted would be high, and definitely it's going to affect our model. And in the testing points also, when we are figuring out the MSC, we have y actual minus y predicted that we are calculating. So yes, linear regression is sensitive to the outliers. So linear regression is affected by the outliers. Then before applying linear regression, multi-collinearity should be removed because it assumes that there is no relationship between independent variables. Yes, linear regression wants that the independent variables are actually independent. So yes, these all three are true, and hence the answer is all of the above. Okay, let's move on to the next question. The value of r square dash with addition of every independent variable. So as the features increase, the value of the r square increases. So it always increases. Okay. Now I will cover a bit of mathematics. This is completely optional. Like, how do we figure out the right values of W0 and W1? The mathematics that I do it here, it's completely optional, but you should understand what's the gist of it. You should not remember the mathematics, but you should understand the concepts that I'm discussing here. Okay? So the error function. The error function that we write is summation y actual minus y predicted whole square. So basically for the training points, we want to figure out summation y actual minus y predicted whole square, and we want to minimize it. We want to minimize it, right? So let's put a 1 by n here also because that's the constant, and we'll have mean square error, right? So this is the error function or the cost function that we have. So we want to minimize 1 by n summation y actual minus y predicted whole square, right? Now, let me write it in a better way. So y actual, I'll write it as y only, and y predicted, I'll write it as w0 plus w1x. Okay, right? Because y predicted will essentially be w0 plus w1x. That's how we want a model to be, and we want to figure out our w0 and w1. Here we are assuming that we have only one x and one y. That is, we have simple linear regression. Now we want to minimize this, right? Now, when the function is convex, so first of all, what is convex function? So if you have any 2 points, just draw any 2 points on the curve, and if those 2 points, when they're connected by a straight line, when you connect the 2 points, and if that straight line is above the curve, see this line is above this curve, right? It's above this curve. So if the straight line is above the curve, then it is called convex function, right? It is called convex function. And if we have a convex function, then we can solve. We can solve the function to get the minimum point of error, or sorry, the minimum point. We can actually get, if we have a convex function, we can get the global minima or the minimum point. In our case, the function is error. So basically this function, I'm not proving it, but this function is basically a convex function. That is, I can solve this to find the point, the minimum point or the global minima, the minimum of the minimums. I can figure out where, at what point, at what W0 and W1 value, I am going to get the minimum cost function or the minimum error function. So this function is convex, and only when the function is convex, it will have a global minima, and it is solvable to find the point of minimum. Okay. So this is a convex function. So only thing I wanted to tell here with the convex function is that, hey, this function is convex, and that's why we can solve it to get the minimum of the minimum point. That is basically find out the W0 and W1 which minimize this. So this is, so all functions are not solvable, but all functions are not solvable to get us the global minima. But this is going to be solvable to give us the global minima. Okay. So now we have to minimize this error, right? So how, since we have to minimize this error, the first derivative should be 0. First derivative with respect to W0 and first derivative with respect to W1. Both should be 0. Both should be 0. Now, from here, we will get one equation, and from here, we will get another equation. This here, we have one equation, here we have another equation, and we have two variables that we want to figure out, W0 and W1, right? So basically, when we solve these two equations, I'm not doing the solving because that's not important, but I want you to get the feel of it, right? So basically, what do we do is we uh, we figure out the W0 and W1 from the two equations. So the first equation I have is that the derivative with respect to W0 will be 0, and the second one that I have is the derivative of this error function with respect to W1 will be 0, and I can figure out the W0 and W1 from here because there are two equations. Okay, and from here, guaranteed we are going to get our W0 and W1. That W0 and W1 that which minimize the error, and that's what we basically need. If we have the W0 and W1 which minimize our error, let's say W0 is 3, W1 is 4, then 3 plus 4x is actually our linear regression model, the one that minimizes the error. But this solution, like finding the derivatives, equating it to 0, and then figuring out our W0 and W1, this has higher time complexity. That means it takes lot of time to figure out. So if our data set is very high, because we have to take the summations, right? And then we have to solve these two equations. So this has high time complexity. That is the time taken by figuring out the W0 and W1 in this way is going to take a lot of time. Obviously, it's going to give you the exact solution. It's going to give you the exact W0 and W1 values, which minimize your error. They are going to give you your exact best fit line. They're going to give you your exact linear model. But the problem here is that this solution has high time complexity. It takes a lot of time. So we can use this if we have a small data set, but if we have a big data set, then it takes a lot of time. So alternatively, we have some approximate solutions. So this above method is called the normal method, solving the equations to find out the exact values of our intercept and the coefficients. It's called the normal method, but it has high time complexity. So we have some approximate solutions also. The first one is the gradient descent. The first one is the gradient descent. Okay. Now in gradient descent, what we do is we randomly select the values of W0 and W1. We say, hey, we start off with W0 as 4 and W1 is, let's say, 6. And then what do we do is we keep on updating our W0 and W1. We keep on doing that, and we do it for multiple iterations. How do we do the update? So the new W0 becomes W0 minus dou E by dou W0. Differentiate error with respect to W0. And then here we have a learning term also, learning rate also. I'll talk about this learning rate in some time. Okay. So we have W0 minus eta, this is called eta or the learning rate, dou E by dou W0. And we have our W1 updation as W1 minus eta dou E by dou W1. Both are same. One is for W0, other is for W1. If you have more constants, W2, W3, W4, and so on, then you are going to have other equations also. Now, this is the update that you get in the first iteration. then you get the new W0 and W1. Then in the next iteration, you further figure out your new W0 and new W1. So you keep on finding out the different W0 and W1s. And then you finally, after some iterations, let's say 100 or 200 iterations, you get close to the global minima. For example, let's talk about W1 and the error. Let's say the graph is like this. So let's say we took the W1 to be here and the corresponding error was here. Now what do we do is in every update, we slowly move down. We slowly move down, and after multiple iterations, we would come to a point here, somewhere here, which is very close to the global minimum. Okay, you can do a lot of iterations, but what happens is initially the movements are fast. One second. So initially what happens is first the steps that you take, the first steps that you have, they have the decrease in error is high. But as you slowly move here, the decrease in errors becomes small. Okay, so that's why we fix some iterations, say 100 iterations, and whatever we get after 100 iterations, whatever value we get out of W1 and W0, we are going to take that. Obviously, it's not going to be the exact solution, but it's going to be an approximate solution and it's going to take lesser time. And we'll be very close to global minima. We might be here, but the global minima is here, but we are very close to it. Okay, so this is what gradient descent is. This is what gradient descent is. Now, what about this learning rate? Basically, this learning rate tells how are we going to move? Are we going to move very fast or are we going to move very slow towards the global minimum? So if our learning rate is very high, it's a problem. What happens is we started from here, but if our learning rate is very high, we actually don't go down, but we move to the other side. We go here, then we, instead of convergence, we are continuing to diverge. We just keep on changing the sides. So our learning rate should not be very high, right? Because if our learning rate is very high, then we might get uh, we might not be able to reach here. We might not be able to reach here. Okay, so we want to reach here. Okay, so basically if our learning rate is high, we might just be switching the sides. Now if our learning rate is very small, then the problem would be it's going to take baby steps, very small steps, and it's going to take a lot of time to reach somewhere close to here. So our learning rate neither should be very high, neither it should be very low. If our learning rate is very small, it would take more time to reach the global minima, that is more iterations. And if eta is very large, then we might actually just be changing sides, that is move from one side to the other. We might uh, we might not be able to reach the global minima. Okay. Now this is gradient descent. Obviously, this is a way in which we are able to figure out our approximate W1 and W0 and W1, which give us almost the least error, not the exact least error, but they give us the approximate solution. They give us the approximate W0 and W1. That is, they give us an approximate model, right? But we can optimize this further also. So in gradient descent, what do? We figure out the dou E by dou W0, right? We figure out dou E by dou W0. And here, if we see the dou E by dou W0, let me show it to you. Let's actually figure out dou E by W0 once to get a better idea. So dou E by dou W0. So basically it will be dou by dou W0 of 1 by n summation y minus W0 plus W1x whole square, right? It's fine if you are not able to remember the differentiation, that's okay. Okay. So now 1 by n is a constant, so it comes out. So we have dou by dou W0 and summation will remain as it is. And when we try to do this, summation, basically the differentiation of this. I'll just tell you the differentiation. It's fine if you're not able to understand it because it's going to apply some chain rules. Okay. So basically, first you do the differentiation of this. So the differentiation of y minus w0 plus w1 x whole square. So first what happens is you take this y minus w0 plus w1 x as some variable called z. And then you write it as twice y minus w0 plus w1 x. And then you do the differentiation of first of y. So differentiation of y with respect to w0 is going to be 0 because it's not affecting your y, right? Your w0 is not affecting your y. Then when you differentiate it with respect to minus w0, you're going to get a minus 1. So differentiation of minus w0 with respect to w0 is going to be minus 1. And then when you try to differentiate w1x with respect to w0, you again get a 0. You again get a 0, right? So this is going to be your differentiation. So it's going to be minus 2 by n summation y minus w0 and plus w1x. Okay. So if I remove the right, if I remove the parenthesis, so it looks like this, right? Now the point is that if I write w0 dash is equals to w0 minus eta dou E by dou W0, which I now know is this, right? I know it's this. Now, the point is that here we have the summation that is for every updation. We need to figure out that is we need to take all the y's and the x into consideration of the training points, and we need to scan the entire database to figure out this dou E by dou W0, right? Because we have all the points. We have all the points, right? If you want to just remove this minus sign, it would be, so if this minus sign goes away, it would be 2 by n, and we'll have w0 plus w1x minus y, like this. Okay, so this is the update, right? Here, if you see, to find out W0 or W1s at each point after each iteration, you basically have to scan the entire database, and the database can be very big. So basically, you need to see what is the X and the Y for the first point, what is the X and the Y for the second point, and you need to continue doing it. That is, scan the entire database for each iteration, right? Which is going to take some time, right? So we have something called as stochastic gradient descent, which is a optimization over gradient descent in terms of time. Obviously, gradient descent is going to perform better, but stochastic gradient descent is going to help us decrease the time. So instead of doing the summation for all the points of the training data, just randomly pick a point. Don't don't do the summation. Just randomly pick a point, and for that point, just figure out what W0 plus W1x minus y is. That's it. Don't do the summation. You just randomly pick a point. Obviously, in the first iteration, there could be one point. In the second iteration, you can pick another point. In the third iteration, you can pick another point. But what you have is, don't do the summation, just randomly pick a point. That's it. And your eta values are generally zero point 0.1, zero point 0.01, zero point 0.05. These are the general values of eta that are used. Okay, so in stochastic gradient descent, you don't do the summation, but you randomly pick up a point. Also, we are going to discuss a library sklearn which will have inbuilt models for us. We already discussed sklearn a bit. So sklearn is going to be the Python library which will have all these models already built for us. We don't have to do this normal method or the gradient descent or the stochastic gradient descent. We just need to call linear regression, and internally it will have something which is kind of a version of stochastic gradient descent only. So it's going to do a version of stochastic gradient descent internally and help us give the result. So we just have to call linear regression. We don't have to write the code for gradient descent or stochastic gradient descent or normal method. So sklearn inside if we call linear regression, then it's going to build the model for us directly. But I wanted you to understand what internally also happens. What are the different model types? And sklearn by default uses a version of stochastic gradient descent. Okay, so it's called stochastic gradient descent regressor. Okay. So that's all for this session. We have completed linear regression. We understood what is linear regression, how do we build the model. We dived into the mathematics also a bit. Now we understood how we can minimize our error function to find out the W0 and the W1. And that W0 and W1 will actually be the coefficients and the intercept which actually help us get the linear model. So y is equals to W0 plus W1x. We figure out that W0 and W1, which are going to be the best fit line or the linear model, which minimizes the error on the training data. Now, after we have built the model, we are going to test it on the testing data. And for that, we have the evaluation metrics, which are R square, adjusted R square. R square and adjusted R square should be close to 1. And the other two are MSE and RMSE, which should be as low as possible. So that's all for linear regression. Thank you, everyone.